Can you see my screen?
Yes, sir.
Okay. So in the last class, we have talked about these ones, right? So that means basically once we have our data, okay. So basically here I have just shown the data, and then what we have. Just a minute. And then once we have our feature vector, okay. So what we are going to do? So these are basically this means basically we have the eigenvectors, okay. The eigenvectors is basically this ui that we are representing, okay. And then what we'll do, we'll do this projection on these UI. So basically we'll have multiple UIs, and then basically you have your data, okay. So it's like these are basically what can I say, these are arranged in which format, okay, it doesn't matter actually. And then you have your data X. So if you have the dot product between them, basically you will get the projected data, right? Now what will happen, let's say in this example, because since we have seen that in the previous cases, we have seen, let's say in these cases, so one eigenvector will be in this direction and the other eigenvector will be in that direction. And since we are to remove one of the eigenvectors, so if I remove this particular eigenvector, what will happen? Let's say this sample will project here, right? Yes or no? This sample will project here, this sample will project there, and then so on. If it happens like that, so did we lose information? Yes or no? Did you lose information? Okay. So and then since you have taken, you say since you did not take this one, okay, this direction, as I've said, you have excluded. You have only taken this particular eigenvector in this direction. And if you want to do the reconstruction, whatever information you have lost, can you get them back? Is my question clear? Whatever information you have lost, can you get them back? Hello, can you hear me?
Yes, sir, we can hear you.
Okay. So, so I asked you a question. Can you tell me the answer? In
No,
this
you cannot
case,
get
if
it back.
you cannot get it, the thing is that if I look at from this point of view, let's say if I have this particular axis, okay, like this one, this x-axis, okay, this is what we are representing like this first eigenvector u1, and this is what we, so you have for I don't have my tab with me, so I have to write with my mouse actually. So this is u2. Okay, so if I discard u2, then you are losing information from one particular dimension, right? Yes or no? Yes. And if you have lost it, and if you didn't store it, can you get back whatever you have lost? Of course not, right? So that's why you'll see here. So once I have taken k number of eigenvectors instead of n, because from n we have reduced it to k, and then if I want to reconstruct my data, whatever information I have lost, so if you see, you can reconstruct data by taking the inverse of it, multiplying, that means taking the dot product, you will get back the data back. And of course, you have remember that at the very beginning we have subtracted the mean. So if I add back by mean, I can reconstruct the data, and the reconstructed data will look as you can see over here. Okay, this is what you can see over here. So you can see that some of the data was here, right? Some was there, some was here, some was there. That means in the other direction, whatever we have lost, we could not get back exactly whatever we had before, could we? Like we don't have this, we don't have that. Rather, we have ended up with something like that, something like this, or these. So that means you have lost information from one particular axis, right? So that means basically the PCA, if you take less number of eigenvectors, of course you can reduce the feature dimension. The problem you will be facing is basically you will lose some information. Now, if I ask you how much information will you lose? So basically, you had two things. If I look back from the earlier picture from here, so this was basically what the original data was looking like, and this is what you have now. Okay, that means you have lost some information. So from the original to the approximate, if I take the difference, let's say if I just come over here. So if I ask you what is the average projection error that we have, so if I write like this, what's the original data? The original data was represented by X, and the reconstructed data, if I write like this, it was A approximate. If I write like this, okay, A approx means basically the reconstructed data. So if I take the difference, so difference will basically give you the amount of information you have lost. Yes or no? And if I want to take the average square error, so you can see that this term here, this term is basically your average squared error, right? Yes or no? Is this understood?
Yes, sir.
Okay. So fine, that means this is basically the amount of error that we have. That means the information that you have lost. How about the total data in your sample? How much data do you have in your sample? So this is what we are going to do. We are going to say in this way, if I take the magnitude of all the actual data, don't you think that basically I have the total information in my hand? Yes or no? Okay, fine. If that's the case, let's say if your error was zero, that means if this value was not there, then basically the numerator divided by denominator, this would have been equal to what? This would have been equal to 1, right? Yes or no? Correct or not? Okay, but if you have some projection error means basically there is a difference between these two, and since we have some error, the error divided by total amount of information, that is basically what we say is how much information do you have lost in terms of percentage. Can I say like that? Now we can see that if I define the threshold value, let's say threshold value of 1%, or let's say in case of fractional value, because if it is, since it is normalized to 1, so if I like 0.001, that means basically it's 1%. So if we have a reconstruction, and reconstruction in such a way the error is less than 1%, that if I say how much information have you retained, you have lost 1%. So how much information have you retained? 99%, right? Yes or no?
Yes.
Okay, so basically that means if I have all the data, if I have 100% data, that means I have 100% data variance in my hand, if I can say like this. I have 100% data variance, but do I have 100%? No. Since my reconstructed data have lost 1% of information, so can I say that I have retained 99% of the variance? Can I say like that? Can you say like that?
Yes, sir.
Okay. So now the thing is that the question is comes, how will I select, because the title says, how will you select the number of principal components or the number of eigenvectors you will choose? So what can I say? If I pick, let's say if I say, if I pick all n eigenvectors, how much information will you retain, or how much variance will you retain? 100%. So what we'll do, we'll try to reduce the value of this k. Let's say at the very beginning, if the value of k was equal to n, would have retained 100%. So I will try to reduce it as much as possible, and maybe at some point, if I say like this, at some point, maybe for this value of k, if I select like this, let's say for this value, for example, let's say I have picked 35. For this value of k, you have found that still the reconstruction that you have got can retain 99% of the information, or 99% of the variance. So which one is better? If your originally the value of n was equal to 1000, if I say like this, it was originally equal to 1000. So which one is better? 1000 having a variance of 100% or reducing it to 35, that means sacrificing 1% so that you can have a variance of 99%. Which one is better? Second one, right? But you can see that, okay, since if I reduce it even less, let's say instead of 35, let's say if I take 15, for example, if I take 15, now you can see that you have got a variance of, let's say, 95%, for example, 95%. Fine, that's fine. 95% still, which is okay. But if you set your threshold to 1%, so should you take 95% or should you stop at 99%? Exactly. That means basically this is the threshold value. Let's say if I write like this, this is the threshold value that you have to set, the user has to set accordingly to his system performance. If he is satisfied with 5% information lost, or if he can retain 95% information and he still is happy, so you can set the threshold value to what? 0.5, right? Yes or no? That means how much error you are accepting. You are accepting an error of up to 5% error. In this case, maybe you can pick the value of k equal to 15. Is this understood?
Yes, sir.
Okay, this is actually how we consider in terms of error, okay, in terms of projection error. There is a second way to do it, as I've said. So you can do the other way down. You can start with k equal to 1. Then see how much error is it. Does it satisfy? If not, you increase the value of k to 2, then it to 3. And in this way, you stop until you have found the desired level of variance. Understood? But there's another way to do it. I believe you recall that once we do the single level decomposition, we get this matrix. With this matrix, where in the diagonal entries, what values do we have? Eigenvalues. Okay, fine. And I have also said that if I plot the eigenvalues in this way, let's say if I plot the eigenvalues in this way, you'll see that most of the eigenvalues will become close to 0, and a less number of eigenvalues will be significant, like this one. Okay. So if this is the case, and then what I do, if I compute the area under this curve, that means if I compute the cumulative summation of all the eigenvalues, and if I normalize it to 1, or let's say, or I can say like that means I have 100% information. I can consider like this, right? Yes or no? That means if I take all n number of eigenvectors, so how much information will you retain? 100%, right?
100%.
Okay, how about if I say, similar way I've said, let's say I want to retain 99% of the information, and I just want to accept an error of only 1%. If I say like this, and what I do, I check, let's say up to this point, if I say like the area under this curve, that means the area on the left hand side over here is equal to 99%. And on the other side, we have, how much percent do we have here? On the other side?
1%.
1%. Fine. And if we define the threshold in such a way, that means for this particular value of k, we have found that on the left hand side, that means the information that I have retained, this is actually what I will retain, and on this side is basically what I will lose. If I write like this, R means retain, and right hand side means lose, means what I am losing. That means you will stop the value of k at which point? The point where the area under this curve, that means the summation of all the eigenvalues are equal to 99%. Is this clear? Yes or no? So if I consider like that, so what I'm doing, so if you look from here, the same thing what we have done over here. That means up to the k point, that means the threshold value that I have shown you earlier, if I draw like this, okay, just drawing like this, okay, it shouldn't go like that. It should be a nice figure like this. Something like that, okay. So that means if I come up to this point, so up to the k point, starting from the very beginning, starting from 1 to up to k, as you can see from here, the numerator part, if we add up all the eigenvalues, divided by the total number of eigenvalues, that means we're normalizing it. If the value is greater than or equal to 99.99, what does it mean? That means I have retained 99% of the information. Is it yes or no? Is it correct or not? And simply, if I just simply want to say that how much error have I do have. So what should I write then? I can simply write 1 minus this, right? If I write 1 minus this, what will happen? This will become a check simply 0.01. Yes or no?
Yes, sir.
Yes, sir.
That means, and also this condition, if you want to have an error of not more than 1%, so don't you think it should be like less than equal to 0 point something like this? Yes or no? So that means the error, so if I say from the point of loss or information loss, so that means the loss should be a maximum of what? A maximum of 1%, right? That means this part should be what? Should be less than or equal to what? 0.01. Is this clear?
Yes, sir.
Is it clear? Okay. So this is actually how you will be picking your choice of eigenvectors. That means you have to have a threshold value up to which point you want to allow the acceptable data variance or acceptable, I mean, information loss. Okay. Oh, now, some basic advice for PCA. Okay. So you can see from here what we have done. Let's say we want to do a supervised learning. Okay. And then let's say the original samples are represented by X. If the original samples are represented by X, and you can see that X will have this, I mean, feature vector size of 1000, or is it, okay, it's 10,000, right? It's 10,000. So what we can do at the very beginning, we can consider as unsupervised learning technique and just forget about this, I mean, class levels Y for the time being. And then we can apply PCA. We can reduce the feature dimension. Let's say we have reduced it to maybe, as we have seen talked earlier, that means we have reduced it to 35. So in this case, have we significantly reduced our feature dimension? Of course, yes, right? That's exactly what we have done. And then based with this new transformed data, what we'll do? We can go for training. That means we'll go for training with this supervised algorithm, for example. Then this will go onto a neural network. And then we can basically do the training and so on. Is this clear? So if I do this, what kind of benefit do I achieve? What do you think? What kind of benefit do you achieve? You simply have a speed up, right? Yes or no? Can you hear me? So whatever I have said, do you agree with me or disagree? Okay. So that means if I had done PCA where I had retained 99% of the information, so that means basically I am just sacrificing 1% so that I can have a significant reduction in the number of feature elements, 35. That means with these new features, we have a significant speed up to train this, let's say, subsequent supervised method, that is, let's say, neural network or regression or any kind of other supervised method actually. Is this clear? Now we have a second question here. This is what we have done for training. What should we do for testing? What do you think? What should you do for testing? Or even for the validation set? What should you do? Is my question? So okay, if I say like this, okay, let me draw over it. Let's say what we did for the this is training. Okay, this is training, and for the training set, what we have this sample X. Okay, we had done PCA. So once we have done PCA, we have this. I mean, this is Xi. Then we have this Zi, which we have done PCA. So over here we have done PCA. Okay, we have done PCA over here, and then with this Zi, let's say we have applied neural network, and then basically we have got the predicted outcome. Of course, we have the, this is Y actually. Okay, you have the actual Y. This is actual Y. Okay, so this is a comma over here. I should remove this one, probably it doesn't look good. Okay, I lost everything. Anyway, so that means if I have, let's say in case of test, let's say in case of test, what will I do? I will do the same thing, right? I will have this sample X. This will go to the step PCA. But once I do this PCA, we know that we have to compute this covariance matrix. Yes or no? Right? Do you understand what I'm saying? Can you recall in case of PCA, we have to find this covariance matrix sigma. And this from this covariance sigma, we have to compute this eigenvector UI, right? Yes or no? Okay, fine. But if I do the testing, let's say I give you one sample, only one sample is there. So can you do PCA with one sample? Can you perform PCA with one sample? Of course not, right? Because you have to compute this covariance matrix. But this is the thing. In case of testing, the eigenvectors that you had from this training step, that eigenvector will come directly over here. And then you simply do the projection on those eigenvectors. Let's say U1, U2 up to UK. And then you will have the corresponding transform data in the Z space, and then you can apply this neural network, and then basically you will get the output Y hat. Is this clear? Yes or no? Is this clear? Up to this, do you have any questions? I believe you should have some questions here. Okay, let me ask question. Khalid, can you hear me? No? Okay, how about Fayad, can you hear me? Fayad is in this section, right? Hello, any of you, can you hear me?
Yes, sir, we can hear you.
Okay, okay, then let's say Akib Mohammed. Can you unmute your microphone?
Yes, sir.
So in this case, let's say in case of the training data set, we have this covariance matrix. We had computed this eigenvector UI, and that's how many eigenvectors do you have to store if you want to do the testing? How many
Can
eigenvectors do you have to store if you want to proceed with the testing? All n number of them or only k number of them?
only K number
Okay, so why did you take only k? Why not all of them?
to reduce the dimensions?
Okay, to reduce the dimension. Okay, that's true. But the thing is that what you have to do is that you can see that once you have used this neural network, this neural network had to work with in which space, in the X space or in the Z space.
In the Z space?
Okay, that means during this training phase, this neural network worked with which data? The data in the Z space, right? So
Yes.
if I don't use this PCA, can this neural network work with the data in the X space?
No, sir.
No. So that's why you have to do PCA. And if we do PCA, basically, which step will you follow in case of PCA? Only the projection step, right?
Yes, sir.
Do we need to go again for choosing the eigenvalues?
No, sir.
No, because whatever the projections you have done, you have to pick the same projection space for the test or validation data too. Is this clear?
Yes, sir.
Okay. So here is another thing. Basically, what we do normally, you'll see that in the literature, we'll see that you can use PCA to reduce to overfitting. This is what sometimes you will see in the papers. Even I myself, I have done this because at that time I didn't know that whether it will reduce the overfit or not. Because I thought that if I apply PCA, if I reduce the feature set, because we have learned in the first classes, the first few classes that if we reduce the features, we can reduce overfitting, right?
Yes, sir.
Fine. So we know that now if we apply PCA, I can reduce the number of features. If I reduce the number of features, then we see that with the few number of features, it is likely that we'll reduce the overfit. Yes or no? Yes or no?
Yes, sir.
But this is not true actually. Why this is not true? Can someone tell me why it is not exactly true? The thing is that in case of normal feature selection, let's say you had started with, let's say for example, let's say the original feature set that you had 10 features, and then by reducing the number of features, you only pick the significant 4, and then you say that okay, by reducing the number of features, we have reduced overfitting. Let's say in case of regression. Is this true? Is this true? Yes or no? Do you understand what I'm saying? The original feature set was 10, then you did feature selection, you picked a new number of features, that means only 4, and then we say that with since we have reduced the number of features, we can reduce overfitting. Is it true or not?
Yes, sir.
And why is that? Because if I discard 6 of them, I have discarded 6 of them, so basically I'm also discarding some amount of data variation, right? Since I am discarding certain amount of data variation, I am also trying to reduce the overfitting problem over here, right? Yes or no?
Yes, sir.
Okay, let's look at from the point of PCA. This is what we have done in case of normal, let's say, feature selection. In case of PCA, I do the same thing. Let's say I start with 10 features. I did feature selection in terms of dimensional reduction, but I have retained 99% of the data variance. And by doing that, I have got the new set of features, which is now, if I write like n dash, which is now 4. The question is that I did reduce the feature dimension, but in terms of data variance, have I reduced the data variance?
No.
So in this case, do you think that you have got the idea that now you can reduce the overfit? Yes or no? Yes, because then basically since the data variance is still there, and with this variance, still you want to fit the model with this variance, what will happen? You will still have overfitting. Is this clear? Then
Yes, sir.
basically we can see from here, then basically, I mean, sometimes it might work, sometimes it might work, but it's not a way to basically address overfitting. Since the data variance, you haven't reduced the data variance. So what should you do actually? Basically, if you want to address this overfitting problem, you have to go for normal regularization factor. Is this clear?
Yes, sir.
Okay. So the thing is that, okay, so now basically we said the why should we apply PCA then? What do you think? If we consider like when to apply PCA. So we can understand from here. First of all, PCA, if I do this dimensional reduction, I can retain as much as original data variance, that means data information. At the same time, I can speed up my next learning algorithm. Correct? Also with the same information or almost the same information, since the dimension has reduced, the feature number elements have reduced, I can also have less memory or space to process or manipulate the data, right?
Yes,
So
sir.
that means this falls into the domain of compression. That means I have compressed the data so that I can speed up, I can transmit, I can store in less time and space. But in terms of data visualization, what we do, let's say if what we have over here, let's say if the dimension is something like, even if it is like 10, can you plot this data? Can you plot this data on a computer screen? Of course not, right? We can maximum we can plot a data dimension of what? Data dimension of 3 or maybe 2. Yes or no? right? So the thing is
Yes,
that
sir.
if I can apply PCA, I can retain the data variance, let's say, and I can reduce it to 3, and I can simply plot it to see how much the data has been distributed in that space. Can I have an approximation of the data distribution in the original space? Yes or no? That means PCA can help us to visualize. That means we can reduce the data from the high dimensional space to 2D space or 3D space, and then we can plot it, and then we can try to have an understanding of how the data are being spread over there. Is this clear?
Yes, sir.
Okay. Anyway, so sometimes you see that people will try to, as I've said before, that people try to apply PCA to reduce the feature dimension, and then they will go on to do some supervised learning, for example, logistic regression or regression. Okay, and they will train it and they'll do the same thing for testing and see how much performance they have achieved or not. The thing is that what you should do is we should consider that without PCA, whether I have the same performance or same result or not. Okay, and then you do it. That means you don't do it. Okay, you don't do PCA. You take your original data. That means you do your regression with this original data. Okay, and you see whether you have the same performance or not. Okay, if you see the performance is same but the speed up is significant, then you can go on for trying applying PCA. Is this understood? Is this understood? That means basically what you should do, first you apply without PCA, see your result, then you run PCA, and then you see whether you get the same result or not. Okay, if you get the same result but you have a significant speed up, then you should choose to use PCA. Otherwise you should not use PCA, because computing PCA itself is computationally expensive. Is this clear? Okay, so this is basically the part where we stop with what can I say, with unsupervised learning on PCA. So up to this, do you have any questions? Any questions on PCA? Okay. So now we'll be starting another one. That is today, basically, I wanted to start it in the previous class though. Can you see my screen?
Yes, sir.
Okay.
Yes.
So this is lecture 14 on clustering analysis, or clustering in short. So basically, this is also an unsupervised method. It's an unsupervised method. So basically, first of all, the definition of cluster. Definition for a cluster is basically it's a collection of objects where samples within the same cluster will share some similarity, and samples from different clusters will share some dissimilarity. Okay. So that means basically clustering analysis is the algorithm or the set of algorithms to find the clusters based on the similarity between data. Okay. And it is called unsupervised method because, as we have seen before, let's say if I give you this data, let's say these are some points over here, and now here we have some points over there. Now, did I say which sample belongs to which class? I have
Yes,
not,
sir.
right? I have not. So that's why this is known as a data without labels. And if I want to apply some learning algorithms here, these will fall into the domain of unsupervised learning. And since I want to define the clusters, that means I want to define the clusters like this. Let's say this is going to be cluster 1. Okay. And let's say this is going to be cluster 2. If it is like that, means this is an unsupervised method, because I have to find these groups by myself. And like you see that all these data, they belong to this cluster, but this sample did not belong to this. Let's say this, if I say this is cluster 1, and let's say this is cluster 2. So now if I say these samples, they did not fall to the cluster 2. Why did, let's say this blue one, if I mark over here, this sample you did not group it into cluster 1. Why not?
Because it was farther away from the members of cluster 1 than it was from cluster 2.
Okay, that means you said further away. Now if I say these samples, you see if I just mark here, let's say if I mark it black at the bit, let's say this sample and let's say this sample, all these samples you have grouped into cluster 1. Why you have grouped them into cluster 1?
Because they're nearer to each other.
Exactly. Maybe you thought from the point of physical proximity or physical distance, right? And whichever is very close to each other, we assign it to a single class, right? And the blue one, since it is far away from the black one, so that's why you try to make a different cluster of its own, right? And then you also find that some other group samples are also close to the blue one, so you clustered them into cluster 2, right? That means basically what you had done, you had defined some similarity measures or some grouping criteria. That means it will give you some characteristics of the data, and accordingly you will group them or you will separate them, right? Yes or no? Okay, so now we'll see that this clustering, it can be used as a standalone tool. That means you want to do the clustering and grouping to understand the data distribution, or it can be used at a data pre-processing step for other algorithms. Like for example, let's say we can do the clustering and grouping, and then we can go for some supervised method and so on. Okay, so we'll just focus on this basic clustering technique over here. So here basically we have some applications of clustering. So I will talk about these applications later too. Just give you some names over here where clustering algorithms can be used to develop different kind of applications, starting from biology to web search to information retrieval to news grouping, even in the website. Okay, you see that in the website, let's say in Google News, you have seen that similar type of news are grouped together. Have you seen it? Yes or no?
Yes, sir.
So what does Google does? Google does basically crawls all the newses, okay, and then basically it does some clustering to group news of similar type. Let's say all the sports news will come together, all the politics news will come together, all the, let's say agriculture news will come together, right? Yes or no? Even you can have the option to group according to the region. Let's say all the news from USA will come together, all the news from Bangladesh will come together, and all the news from, let's say, India will come together. So at the very beginning, did they say which news belong to which category? They didn't, right? But what you'll do, if you do the clustering based on some similarity measures, you can group them all together, right? Anyway, let's see actually how we can do this grouping. Okay, so basically here are some of the application area where basically we can use clustering as a pre-processing tool. You can start from summarization, compression, finding k nearest neighbor, outlier detection, and so on. For example, if I pick this example of outlier detection, let's say you have a credit card and your daily uses or daily, the buying using your credit card is somewhere from 1,000 to 5,000. Let's say if I take the data for the last 100 days, I have seen that your credit card history say that you buy things within the range of 1,000 to 5,000. Now, suddenly, if there is a transaction where it exceeded, for example, let's say it's something like 2 lakh or maybe 2 million. So do you think it's a normal transaction or it's a regular transaction? What do you think?
No, sir.
Okay, it's not a regular transaction. Why it's not a regular? Because all your regular transaction, if I make a group of them, because have you defined which one is regular and which one is irregular? Have I defined earlier? I haven't, right? So if I consider for the last 100 days, all the transactions have been made by me, and if I want to group them together, I can see that my grouping range will be something between 1,000 to 5,000. And suddenly today, let's say today in the afternoon, there is a transaction of, let's say, 2 million. So it automatically signifies that, it's an exceptional transaction, right? That means that transaction can be viewed as an outlier. And with this outlier, it means that it falls far away from your usual cluster or usual group. Now, can you build an application based on this information? Yes or no? Do you understand my question? Can you build an application based on this?
No, sir.
Can you have a automatic fraud detection technique based on this information? It can happen that somehow your credit card has been lost, and let's say somehow your PIN was also written on the card number, and if someone found it, some bad guy found it, and what he will do, since he's got this one chance, or he will try to withdraw all the money from your account, yes or no? So automatically, if the bank can detect this outlier, it can do a secondary check with you, correct or not? So, and if the bank checks with you and if it is an authenticated transaction, because even yourself, you can have a exceptional transaction with an amount of 2 million maybe. So bank will can check against you, and then if it verifies that you are a genuine guy, you are the one who owns this card or this account. So what will happen? It will just simply approve that transaction, right?
Yes,
But
sir.
if it is a fraud person, okay, it's a bad person. So what will happen? If they goes for second step verification, what will happen? Automatically, he will identify that, the bank will identify that it's not a genuine transaction and he can stop it. Yes or no?
Yes, sir.
So which one is better? Sometimes you get annoyed. Okay, why are they sending us some secondary verification? Right? I have my card. They have given my PIN number. It's okay. I go to the ATM booth. I do my withdrawal. So why do I need a secondary check? So which one is better? To sometime to be secondary verified by the bank, or without any verification, maybe once in a year you lose everything. Which one is better?
With secondary verification.
It's better to have sometimes to have some verification, right?
Yes.
At the same time, it also gives you a sense of assurance that the bank wants to keep your money secured, right?
Yes, sir.
Okay. So this is in the bank. They have this kind of system. Automatically, if you do some unusual transaction, okay, the flag comes up. Flag means basically that system detects that okay, this is an unusual transaction. That's where they go for second step verification. That means sometimes they call you directly, or sometimes they send you an one-time password, right? Yes or no?
Yes,
Anyway,
sir.
so let's move on. Okay, let's move on. So now the thing is that since we want to do a clustering, basically we want to have a good clustering. So how do we define a good clustering? A good clustering method basically we usually produce clusters with high interclass similarity. That means I mean samples which belongs to the same cluster. They have to have some high interclass similarity, and samples from others cluster. If I do like this, so this is another cluster. That means this sample will have some significant dissimilarity with the samples from another class, right? Yes or no? Okay. And again, which one is better? To have a compact cluster or to have a loosely coupled cluster? Which one is better? Which one is better?
Sir, I think a compact cluster is better.
Exactly, because if I have a compact cluster, we can ensure high interclass similarity, right? Yes or
Yes.
no? And if you look at this particular cluster, which is very loosely coupled, okay, so you can see that the cluster at this end and the cluster, the sample at this end and the sample at this end, can we say that they will have a high interclass similarity? Yes or no?
No, sir.
Okay. No, right?
Yes, sir.
Also, you have to have low interclass similarity. That means I don't want to have these two clusters to be similar to each other, right? Yes or no? So that means what we want to have, we want to have compact clusters and also clusters that are basically far away from each other, right? Yes or no?
Yes, sir.
So that means the quality of the clustering is basically depends on several measures. First, the similarity measure that you are choosing, the implementation, that means the way that you are finding the clusters, and also at the end of the day, once you have done your clustering, from that clusters you want to discover or you want to extract some meaningful hidden patterns from the data. Yes or no? Right? Okay, let's move on. So see, the very first thing we need is basically the
Sir,
measure which be
we cannot hear you.
used to Can you hear me?
Yes, sir, we can hear you, sir.
Okay, when did I get disconnected?
The thing you told us was that we want compact clusters that are far from each other.
Okay. Can you see my screen? What screen are you looking at?
So it says measuring the quality of clustering.
So I didn't show you this one, right?
No, sir.
Okay. So we have talked already in this way. That means the quality of the clustering it basically depends on the similarity measure that we are using. Now the question is that the quality of the clustering is basically a significant criteria is basically which dissimilarity or similarity measure we are using. So in the often case, you'll see that we are going to use a distance function. Okay, let's say for example a norm 2 distance function, for example the Euclidean distance, or maybe norm 1 distance that means the Manhattan distance, or maybe n norm distance or p norm distance. But the problem is that since we have a lot of different kind of features, starting from let's say x1, x2, up to let's say xn. So do you think all of them will be numeric, because the distance function mostly works better for numeric ones, right? Yes or no?
Yes, sir.
But we know that our feature elements can be Boolean, it can be categorical, that is nominal, it can be ordinal, it can be even vectors within vectors. So in this case, you have to define a distance function which can work with different kind of data types, right?
Yes, sir.
Also, you may want to have different weights for different feature elements. Let's say for x1, xj, you want to give more importance. In this case, what you have to do, you have to set weights accordingly, right? But if you don't give any weights, what does it mean? All of them are equally important, right? But at the end of the day, you have to say whether the cluster that you have obtained is a good cluster or not. It all depends on basically whether it satisfies your part. I mean your goal or not. If it satisfies your goal, then you can say that your clustering result is good. That means basically the answer is typically highly subjective. Anyway, some considerations you have to keep in mind once you are doing this clustering analysis. The first one is the partitioning criteria. It can be single level partitioning or it can be hierarchical level partitioning. Okay. For example, if I want to arrange a football tournament among the students of CSC third year, and I have just made let's say five teams. So can a single student belong to several teams? Yes or no?
No, sir.
So in this case, you have a single level partition. That means a single player can belong to one particular group. Is this understood? But how about if I do some hierarchical partition? It means that even if I have 10 members, I can also have a competition between those 10 members. Let's say, for example, I can have a badminton tournament. Okay. So though you can have a pair, which you have defined a team, but again, you can have a single tournament. I mean, single head-to-head tournament among those, right? Yes or no?
Yes.
So in this case, do we have a single level partitioning or a hierarchical level partitioning? Okay, let me give the example from the example of news. Let's say if I group different kind of news as, let's say, politics, sports, entertainment, and so on. Okay, then basically we have a single level partitioning. But in case of sports, if I further divide into football, cricket, volleyball, then basically what I have done, I have made a hierarchical of news categories, right? That means let's say a article on Leonardo Messi, okay, the football player Messi. So that news belongs to the sports category. Is it true or not?
It's true.
I can also say that this news also falls into the category of football, right?
Yes.
So in this case, what we are having, among sports, we have multiple categories. That is football, cricket, volleyball. Among them, we have picked football. Yes or no?
Yes.
Then again in football, you can have different kind of what can I say, league tournaments, right?
Yes.
Like what do you have? You have these. What do you have? You know,
Uh,
I think like
Premier League, Spanish.
exactly Spanish league is there, La Liga is there, right? So different. Another you have defined another level of partition. Yes or no?
Yes.
So that is basically an example of hierarchical partitioning. But if you have a single partition, that is no further, I mean tree-based partitioning, then that is known as single level partitioning. Understood?
Yes, sir.
There is another kind of example, that is a separation of clusters. Separation of clusters means whether a sample, that means whether the data will particularly belong to one cluster or it should belong to multiple clusters. For example, let's say, for example, if I say like this, you are a student of CEC, right?
Yes.
That means, do you belong to any other departments?
No.
No, you only belong to one particular department, right?
Yes.
Now, if I say from the point of a bank, in a bank we have three kind of accounts. Let's say current account, savings account, and then let's say payroll account. Now, let's say as a client, can you be categorized into one particular account type, or you can have multiple accounts?
You can have multiple accounts.
Exactly. But that means basically you can have your account, which is basically maybe it's a savings account. Maybe at the same time it is also a payroll account, right?
Yes.
So that means a single sample or a single data can belong to multiple clusters
Multiple.
or categories at the same time.
Yes.
It's not like hierarchical partitioning. Okay, what does it mean? It means that two different kind of clusters, you are a member of two different or multiple clusters. But if only one person belongs to one group, that's an example of exclusive clusters. And of course, the choice of this similarity measure or dissimilarity measure, it can be distance-based measure or it can be connectivity-based measure. Okay, connectivity measure basically it will continue the connectivity among the cluster. That means density of the clusters or continuity among the clusters. In case of distance-based clusters, you'll see that it will mostly consider this straight line distance. Okay, that means in this case you will see the clusters will be mostly convex shaped. But in case of connectivity of cluster, you will see that we can also have non-convex shaped clusters. Okay, we'll talk about that. Don't worry about that one. And finally, we can have full clustering and we can have subspace clustering. Basically, full space clustering means, let's say, if we consider all the feature elements, let's say the feature the dimension is something like n equal to, for example, let's say n equal to 100. Okay, n equal to 100, something like this. This is n. So if you consider the whole feature space, then this is known as full space clustering. But sometimes what you can do, you can, instead of taking all 100 features, maybe you take, let's say, for example, 30 of them. You take 30 of them and only considering those 30, you do the clustering. That means you are doing clustering in the subspace. Is this understood? And basically, when do we do the subspace clustering? Whenever the feature space is too high, the feature space is too high, and if you want to do full clustering, what will happen? For a high dimensional feature space, it will be very expensive, right? To reduce the cost, what we can do? We can do a subspace clustering. But if your data itself is originally, the dimension is low, then you don't have to worry about subspace clustering. You can simply go for full space clustering. Is this understood?
Yes.
Okay. So that's why I've written over here. Full space means often it is done in low dimensional space, and subspace clustering is often done whenever the data belongs to the high dimensional feature space. Okay. So here basically I just categorize the different kind of clustering algorithms. The ones that falls with this partitioning approach, this hierarchical approach, density based approach, and grid based approach. So just give you the names. Just have a look. Okay. I just give you a comparative analysis too. But what we'll be focusing in this course is basically we want to do this partitioning. Okay. As we have seen over here, we are going to follow this partitioning approach, and this partitioning approach you will see that we will do this single level partitioning we will do this exclusive level partitioning, and for the similarity measures, we'll be picking a distance-based measure, and also we are going to do full space clustering. Understood?
Yes.
So among these categories of partitioning method, okay, you will see that there are two algorithms we'll be discussing in this course, that is the k-means cluster and the k-medox cluster. This k stands for how many clusters we want to have as an output. We can have a lot of data. Among this data, I want to have in total of, sometimes we can say a maximum of k number of clusters. Is this understood? Okay. And finally, I will just conclude with this word actually. Let's say these samples are in this cluster and these samples are in these clusters. And if I compute this cluster center, let's say this here is the cluster center, the green one, and here is the cluster center for the blue one. Okay. Now, why didn't you assign this particular sample? Why didn't you assign to this cluster? Why didn't you assign to that particular cluster? What should be the answer? Because in terms of this distance measure, it is too far away, right? Yes or no? So let's say if this is cluster 1 and let's say this is cluster 2. So and let's say this is the sample P that we are talking about. So what we compute? We compute the distance from the sample to the cluster center. And if we can minimize this distance, and if we define this as a criteria function, then our objective is to find those particular set of clusters which will give us the lowest error function E. Yes or no? Is this understood? Hello, can you hear me?
So we can hear you, but I didn't get the last thing that you said about minimizing the error function based on a cluster center.
Okay, the thing is that for this sample, let's say the sample, the black one I have drawn over here, the P, in
So
which
we
class?
can see the screen.
Your screen has gone blank.
Oh, you cannot see my screen?
It went blank just around 10 to 15 seconds ago.
Oh, how about now?
Yes,
Can
we
you
can
see?
see it now, sir.
Okay, let's say this sample P. Why did you assign it to cluster 1 instead of cluster 2?
So because it was closer to the objects in cluster 1.
Okay, because you wanted to ensure high interclass similarity, right? Yes or no? So if we
Yes, sir.
consider the cluster center, C1 is the cluster center of cluster 1 and C2 is the cluster center of cluster 2. So if I compute the distance with respect to C1 and C2, which one has the lowest distance?
C1,
C1,
sir.
right?
Yes.
And if C1 has the lowest distance, can't we say that basically we are ensuring that there is more similarity here in compared to cluster 2? Yes or no?
Yes, sir.
That means if we consider this as an interclass similarity, that was your objective. Since I'm computing the difference, so that means lower the difference means higher the similarity, right? Yes or no?
Yes. Yes.
Yes, sir.
And that means if you define a function E, okay, and this is basically the function that is being used to do this partitioning, that is this criteria function, then your objective will be to reduce this function value, right? Yes or no?
Yes, sir.
That means you want to assign sample to that particular cluster, whichever is the closest to it, right?
Yes, sir.
And if I can do that, can I say that I'm ensuring that I will have high interclass similarity?
Yes.
Yes,
Sir.
sir.
Okay. At the same time, if I don't assign it to the class which is far away, don't you think that I can also ensure low interclass similarity?
Yes, sir.
Intermal means what? Let's say this is somewhere is there. So let's say the cluster center is there, and then here you have a sample. So if I will not assign to this class because why?
That's too far.
because the similarity is very low. What will I have? I want to have another cluster maybe on this side, right? And if I assign to this particular cluster, let's say this is the cluster center, what do I have here? I have high interclass similarity over here, right? Yes or no?
Yes, sir.
So that's why we have defined a objective function like this, where I will want to assign the sample to that particular cluster, which will give us the lowest distance. Understood?
Yes.
Yes.
Okay. Okay, so I think we can stop over here.
Yes, sir.
Okay. So role 17 and role Sao, are you in this course, in this class?
Yes, sir.
So
How are we going to divide today's presentation?
can you meet me on Wednesday?
I don't know.
Okay. At
Okay,
what time?
role 17. Are you inside the campus?
Okay. I hope for me.
Hello, I cannot hear you.
Sir, are you talking about row 70 as in 70 or 17 as in 17?
17, 17, the one who hasn't given his midterm exam.
Sir, 17, Afif is in section A, and I think he had, I think he told the department, I think he sent you an email as well. He was affected by COVID.
Yeah,
So
COVID. So
I'll
that's why
tell him to get in touch.
I'm going to have some makeup exams for them. So that's why I need them to.
Okay,
Okay,
sir, I'll tell him to get in touch.
yeah, tell him to communicate with me. Okay. If he's in the campus, he can also meet me in person on Wednesday. Okay.
Okay, sir.
So I have given the link to your attendance. Have you got it? I believe yes.
Yes, sir.
Okay. Okay. Thank you very much. So we can end over here.